So please just a moment. My PC is stopping. I cannot share the slide. Okay. Oh, I cannot share. Oh, here it comes. Sorry. Can you see my slide? Okay.
Not yet, but
Not yet?
in progress. So yes, okay, good, perfect.
Oh.
Yes.
Sorry.
Yes, please.
Jay.
Oh.
Thank you, Kabat-san, for kind introduction, and thank the organizer for giving us an opportunity to talk about our activities. I'm Yuichi Igarashi from NEC Corporation, and also NEC AIST, Quantum Technology Cooperative Research Laboratory, the National Institute of Advanced Industrial Science and Technology. Today, I will talk on behalf of all the persons concerned. As you know, there are many candidates for physical realization of quantum computing, such as trapped ion, semiconductor quantum dot, and optical quantum computer. Among these, superconducting quantum computing is one of the most promising candidates. Because a superconducting circuit is a solid-state device and fabricated by a semiconductor process, it is scalable. And also, it has already relatively long coherence time on the order of 100 microseconds. A drawback of superconducting circuit is that it must be cooled down to about 10 millikelvin to avoid thermal excitation. Superconducting circuit is used for both gate-based quantum computers and quantum annealing. By using quantum algorithms, it is theoretically guaranteed that the gate-based quantum computer can solve some kind of problems, such as factorization or database search, much faster than classical computers. Therefore, many tech giants like Google, IBM, Intel have invested a huge amount of money in research and development. In 2019, Google announced that they have achieved quantum supremacy by using their 53 superconducting qubits. In contrast, quantum annealing is specialized for solving combinatorial optimization problems. This schematic shows a mechanism of quantum annealing. I guess I don't need to explain this anymore because participants of this INQA seminar would be much more familiar than I. Quantum annealing machine based on superconducting circuit is developed and already commercialized by a Canadian venture company called D-Wave. It is also developed in Europe by Abacus project and also in the United States by IAPA QEO project. In order to read out a weak signal of a superconducting qubit, cryogenic amplifier called Josephson parametric amplifier is commonly used. JPA is also a superconducting circuit. It is composed of a constant capacitance and variable inductance, as shown in the left figure. JPA can amplify small microwave input signals with adding only minimum amount of noise allowed by quantum mechanics. When pump microwave signal modulate the inductance at twice the resonant frequency omega 0, signal is mixed with an applied pump, and energy of the pump is converted into signal, which provides gain. when gain becomes larger as modulation amplitude increases. And when the pump power exceeds the threshold, JPA starts to self-oscillate even without an input signal. In this case, the device is called a Josephson parametric oscillator, JPO for short.
Igarashi-san, so
yes.
Okay, so your microphone is not so stable. I mean that
really?
sometimes we can hear very well, but sometimes it's not so good. So can you check the connection of your microphone to your computer? A little bit unstable. So
how about this? Can you hear me?
Yes, I can hear you, but a little bit not so good, I guess.
So should I change the microphone?
Closer to your mouth, maybe?
Mouse? Can you hear me?
Yes, great, perfect. Yes,
is it
please
stable?
continue. Perfect, yes, looks stable. Yes, please continue.
Okay, sorry about that. So next I will explain about JPO. And in order to read out the weak signal of a superconducting qubit, I already explained this. Skip this one. And this one. So the flux-driven Josephson parametric oscillator consists of superconducting capacitor and a superconducting quantum interference device, SQUID for short. SQUID is a superconducting loop containing at least 2 Josephson junctions, as shown in the left figure. SQUID behaves as a single Josephson junction with a variable inductance by applying external magnetic field. The external magnetic field can be induced by applying an electric current to the pump line, which is inductively coupled to the SQUID. So JPO is a frequency tunable LC oscillator as shown in the middle schematic figure. When we apply DC current to the pump line so that the magnetic flux is at this point, flux bias dependence of the resonant frequency has a slope. So if we apply an AC current in addition to the DC current, we can modulate an resonant frequency. And when this AC pump frequency omega p is almost twice the resonant frequency omega r, JPO starts self-oscillation. This parametric oscillation is often explained by using a playground swing as an example. When we ride a swing, we squat and stand up 2 times during a single cycle of the swing. This squatting and standing corresponds to modulation of the frequency of the swing. JPO has 2 oscillation states with the same amplitude and well-defined phases, 0 or pi, namely 0 pi state and 1 pi state. These 2 states are technically referred to as coherent states alpha and minus alpha. If there is no input signal, the 2 states emerge randomly with the same probability. So it is known that these 2 oscillation states can be used as two basis states of a qubit. In general, when we think about implementation of physical qubits of the quantum annealing machine, the larger number of qubits becomes, the harder it is to realize all-to-all connectivity as a hardware. In order to overcome this difficulty, scalable architecture with full connectivity was proposed by Lechner, Hawk, and Zora. This architecture is called LHZ architecture, which is named after these three people. This is Hamiltonian of the Ising model. In the LHZ scheme, product of the two logical spin sigma I, sigma j is represented as a single physical spin sigma ij tilde. And logical n spins are reconfigured as n-1 over 2 physical spins. In this architecture, we need only local, I mean neighboring interaction for sigma ij tilde to achieve all-to-all connectivity for the original Ising spins. However, in order to guarantee reconversion to the Ising spins, constraints are needed. I will briefly explain about the constraint. As you know, sigma I is either +1 or -1. So the sigma I squared is always +1. If we think about 4 logical spins, product of sigma I squared, I mean sigma I1 squared, sigma 2 squared, sigma 3 squared, sigma 4 squared, is also +1. And this equation can be rewritten by using sigma ij tilde like this. Now look at these 4 physical spins, which are surrounded by dotted box. The lower equation tells us that there should be even parity for these 4 spins. I mean, the number of -1 physical spins is limited to either 0 or 2 or 4. This is a constraint. And if we call these 4 spins as a unit cell of the LHZ scheme, every unit cell should have the same constraint. The constraint is also called as four-body interaction. Then how to achieve the four-body interaction as a realistic physical system is not so easy at all. However, fortunately, if a JPO is adopted as a qubit, it can be realized by a Josephson junction. This is proposed by Shruti-Puri. We improved Puri's circuit a little bit, but basically, it is fair to say that based on her idea, we are trying to realize a quantum annealing machine. Next, I will explain about the sample fabrication. The right figure shows an optical microscope image of a 1 qubit device. First, we evaporate a thin film of superconducting niobium on a high resistivity silicon wafer. By using an I-line lithography and dry etching, we make patterns of coplanar waveguides and a JPO. This cross-shaped pattern, surrounded by a red dotted line in the right figure, is a JPO, which is often called as JXMON. An inset shows an electron microscope image of the squid. The XMON pattern is terminated through a squid. Josephson junctions in a squid are made by shadow mask evaporation and in situ oxidation of aluminum. Each JPO has an input-output line and a pump line. Please compare the right picture with an equivalent circuit schematic shown in the left. The I/O line is capacitively coupled to one of the branches of the XMON, and the pump line is inductively coupled to the squid. Now I move on to explanation of our experiments. First, we use a network analyzer to measure a reflection coefficient S11. The upper left graph shows an absolute value and a phase of S11. We can see a dip in the middle of the graph. fitting S11 by a theoretical equation allows us to know the resonant frequency omega r and the quality factor of the resonator. Next, we do the same thing with applying DC current to the pump port. This allows us to plot flux bias dependence of the resonant frequency. We can make sure that the theoretical prediction is well replicated by the experimental result. Next, we observe pump power dependence of the reflection coefficient. As you know, a harmonic oscillator has eigenstates with equal energy spacing of h bar omega 0. In contrast, due to a non-linearity of a Josephson junction, energy spacing of eigenstates 2 and 1 is different from that of 1 and 0. This difference is called Kerr nonlinearity K. When we increase the pump power, excitation from 0 state to 2 state occurs by 2-photon absorption process. This 2-photon absorption process can be seen as a secondary dip in the power dependence right here. From this, we can estimate the Kerr nonlinearity K value. After measuring basic properties of a JPO, we seek the best self-oscillating condition. With applying an RF signal whose frequency is about 2 times the resonant frequency omega r, we measure an output oscillation frequency omega r, output oscillation signal by a spectrum analyzer. The left figure shows an intensity of the self-oscillation as a function of detuning delta omega and the pump power. Here, detuning delta omega is defined as omega s minus omega r. This result tells us the best condition of parameters for self-oscillation of the JPO. Next, by using the parameters fixed as explained in the previous slide, we perform a time domain measurement. More specifically, we apply a pump RF pulse and detect a corresponding parametric oscillation signal by so-called heterodyne measurement. We repeat that process typically thousands of times and finally get a 2-dimensional histogram of the output plotted on the IQ plane. Here, the distance from the origin denotes the amplitude of the signal, and the angle denotes the phase of the signal. So the bottom right figure means that we observe 2 equally distributed peaks with an equal amplitude and different phases shifted by pi. This is exactly what we expect for JPO. As I said before, a unit cell of the LHC scheme is composed of 4 qubits and a 4-body coupler. Recently, we have fabricated a unit cell device and tried to demonstrate the 4-body interaction and its annealing operation. The results are positive. However, there remains many open questions. So we think that it is not adequate to show you the results yet. We need more experiments and theoretical simulations. Finally, I will talk about 3D packaging technology. Because so far, the number of our qubits is small, we can 2-dimensionally wire an I/O line and a pump line to each qubit. However, as shown in the bottom left figure, when the number of qubits become large, we cannot access to inner qubits by 2-dimensional wiring. So for the large-scale integration, 3D packaging is necessary. There are several ways of 3D packaging. We adopt flip chip bonding technology. In this presentation, we call the silicon chip, where we fabricated JPOs as a quantum chip for short. we flipped the quantum chip upside down and bonded it to an interposer by so-called surface-activated bonding. We choose to vertically access to all the qubits by capacitance and inductive couplings between the quantum chip and the interposer. By using a through silicon via in the interposer and probing socket structure, we realize vertical wiring to a printed circuit board. Then signal lines are fanned out in the PCB. These are measurement results of our 3D integrated structure. Our bottom left figure shows the flux bias dependence of the resonant frequency. It looks like the vertical I/O and pump couplings work well. We also demonstrate parametric oscillation in the frequency domain measurement and heterodyne detection of the parametric oscillation in the time domain measurement. Let me summarize my talk. We adopt the Josephson parametric oscillator and the LHZ scheme to realize a quantum annealing machine in the future. We can use two oscillating states of a JPO as two basis states of a qubit. By using the LHZ scheme, all-to-all connectivity can be realized by local interaction in exchange for the forward interaction. Right now, we have demonstrated basic behavior of a single JPO. If you are interested in a single JPO experiments, please refer to our PRA paper. Finally, we also studied that and developed 3D packaging technology for the large-scale integration. These are acknowledgements. That's all. Thank you very much for your attention. I will be happy to take your questions.
Okay, good. So thank you very much for your very interesting and nice talk on the superconducting parameter-based quantum annealer. So, okay, so now the session is open. Question and comment. Alex, yeah, please.
Thank you. My first question is, how are you going to evaluate the total coherence in your system? And what is the decoherence time in your qubit? Simply because it is based on time-dependent oscillations, there is a potential for more dissipation and decoherence in the system.
Yeah, thank you for your question. That's a very good question. And coherence, you mean coherence as a T2 time, I guess.
Yes.
But actually, frankly speaking, we cannot measure T2 time right now. And we can measure, of course, we can measure T1 time. And recently, the theoretical paper was published. Due to, according to its paper, there is some kind of spectroscopy measurement to evaluate T2 value. So we are trying to use this method to evaluate T2 value, but right now we have no data yet.
I see. And so you don't have yet strategy for evaluating or estimating the T2 time for the system of more than one cell?
No, not yet.
Okay, thank you.
Good. So any other question or comment? So please use raise hand button or switch on your microphone.
Yeah, I have a question.
Yes, Fabian.
On slide 8, the next slide, I was just wondering, how do you define here the best optimal condition, let's say, just by the lowest power, or why do you choose this point?
Oh, so basically the best condition means the output oscillation power is the maximum point. So this it is the color plot, and the blue region is have the highest output power. And also the this line is the threshold. I mean the threshold power, pump power. So the pump power, it is preferred to that. It preferred that the pump power is lower. Is the
I
lowest.
see. Okay, lowest pump power and highest
Yeah.
output power.
Yeah,
Okay,
yeah.
makes sense. And then just one more question: how do you apply gates to these JPOs? I having problems to understand, like, how do you rotate on the Bloch sphere?
Oh, I see. So in this architecture, we don't have to apply a gate pulse. So because it is a quantum annealing machine, not a gate-based machine.
Yeah. Okay, so you cannot apply gates at all, actually.
No, not at all.
Or could you? I see. Okay, makes sense. Thanks.
So and in this LHD architecture, and some kind of gate operation between two qubits is represented as a single qubit signal, because in the LHD scheme, this is the coefficient between the product of sigma I, sigma j, and this is represented as a single qubit signal. So by if you want to change the Jij value, we can change the input signal of the single physical qubit. But we don't have the measure. We don't have the some kind of method to rotate the Bloch sphere or something like that.
Okay, thanks.
Okay, good. So maybe next question from Marta, please. Yes.
Yeah, thank you very much. Thank you very much for the talk. I have a question. So I understand that these, I'm not very familiar with GPOs. And as far as I understand, I see that these can embed Hamiltonians that have the ZZ interaction. Can you comment on going beyond the ZZ interaction? Do you think we can do XX and YY with this architecture?
You mean XS interaction or XY interaction in gate-based computer?
For annealing. So imagine that instead of having a Hamiltonian that we want to use for annealing, that it's an Ising Hamiltonian, we want to use a more complicated Hamiltonian. So just one that has XX interactions or XZ or YY interactions. Do you think this will be possible with this architecture?
No, in that sense, it is not possible. We can use only ZZ interaction. Does it answer your question?
Yes, and can I have another question, please? So I've seen a paper, I don't exactly remember the authors, but they use Flux engineering to enhance the connectivity of a GPO's architecture. Have you explored this possibility on top of the LHZ scheme?
I'm not sure. You're saying that. I'm not sure what kind of paper are you saying.
So what they do is they apply periodic modulation to the system to create a virtual connectivity that is richer than the connectivity that you have in the hardware. I think the paper is by Onodera-san, I think.
Onodera-san, Cartecos, yes, actually I know the all coupling by using the Flux engineering. Yes, I know this paper. Igarashi-san, maybe so her question is that is it possible to make the XX or XY interaction by using Flux engineering, applying the periodic oscillation to the system? So maybe it's in principle, I guess it's possible, I guess.
Really?
Yes, that yes, you can check the Onodera-san's paper. Yes.
I was wondering if this was also considered this type of modulation, but yeah, okay, thanks. Thanks for the answer.
Very interesting question.
Thank
so
you.
Anyway, Igarashi-san, please, yes.
Sorry. Thank you for the question, but unfortunately, I'm not familiar with the Flux type of annealing. So I'm going to study that. Thank you.
Thank you. Thank you.
Good. So it's time to finish today's INQA seminar. Okay. So Shanice, do you have any something to inform to us? Next seminar, something?
So the next seminar will be next week, Tuesday. And I will send out an email to everyone in the email list to remind everyone.
Okay.
Yeah.
Okay, everyone. So thanks very much for attending today's INQA seminar. So thank you very much. See you next time. Bye.
Bye.
Thank you very much.
Thank you very much.
Bye. Thank you.